So we are going to talk about lesson number 5, which is continuity. And in our overview, we mentioned that we saw in lesson 4 there are some functions where we could find the limit as x approached whatever the value was, a, by simply just plugging a in. We could use direct substitution. And so in this lesson, we are going to give that ability a name. Basically, if we can do that direct substitution to find a limit, then we're going to call the function continuous at that point. And it really does line up with your kind of intuitive understanding of what continuous means. It's not interrupted, no jumps, no gaps, no holes, no breaks. It's continuous. So your general idea of what continuity would be is probably a pretty useful place to start. So we'll go ahead and start with a couple of definitions. So first, we're going to define what it means for a function to be continuous at a point. A function, f of x, is continuous at a number a. So I'm going to underline that because that is what we are defining. If the limit as x approaches a of f of x is equal to f of a, which is what I was just mentioning. Basically, you can evaluate a limit by doing direct substitution. Our second definition will be if the above condition is not met, so it is not true that the limit as x approaches a of f of x is f of a, then f of x has a discontinuity. At a. So a discontinuity would be a place where a function is not continuous. And then last but not least, oh, no, wait, sorry, those are the two that we're going to define here. So I just want to break down this continuity definition into 3 pieces for us. So the major part of our definition is right here. The limit as x approaches a of f of x equals f of a. So there are kind of 3 pieces of this. So the first one is that the limit as x approaches a of f of x exists in the first place. And similarly, that f is defined at a. So on this side, we have the limit as x approaches a of f of x. That has to actually exist. And on this side, we have f of a, which means that a has to be in the domain of f. And then finally, the last condition is that those 2 values are equal. So we're going to kind of break that down because we're going to look at continuity and discontinuity from all 3 sides. Sometimes we will have a point that's maybe not in the domain, so there will be a discontinuity there. Sometimes we'll have the limit existing, but not equal to the function value. So let's take a look at a couple of pictures on the next page to see some illustrations of these 3 different pieces in action. So I'm going to start with a graph of a rational function. We'll call this a, and we'll maybe look at something that's like a hyperbola, to something like this. Okay. Now, we are going to have, it says in the directions here, state why each of the following functions has a discontinuity at x equals a. So here at a, we're saying that this function, which I should label as f of x, has a discontinuity at a. And why is that? Which of those pieces of the continuity discussion do not hold here? And actually, it's a couple. So first of all, the limit as x approaches a of f of x does not exist. On both the left side, it approaches infinity, and the right side, it approaches negative infinity. But we also have that f of a does not exist. This function is not defined at a because there's an asymptote there, and I don't see any filled in dots anywhere along that point. So there's actually two reasons why this first example is discontinuous or has a discontinuity at x equals a. For our next one, let's draw a straight line that has a hole poked out at the value of a. This will be our f of x. And actually, I'm going to draw my next one at the same time. It looks very similar. But then I'm just going to fill in a dot there at x equals a, but it's going to be in a different place than where the open hole is on the line. So let's go ahead and answer our question. What is it about this second scenario that makes the function have a discontinuity here? So first of all, does the limit as x approaches a of f of x exist? It does. It's whatever, I mean, I didn't label this, but whatever this y value is, we could call it L perhaps, that will be the limit as x approaches a of f of x. So that limit exists. What about f of a? Is f defined at a? It's not. So that is going to be our main reason. F of x, f of a does not exist. Or another way to say that is the function is not defined at a. And so obviously, therefore, the limit cannot exist the function definition because the function doesn't have a point there. And that's different if we go to our third picture, because now the limit still exists and it still would be equal to this point here. And the function is defined. I don't know, let's give it some value here. But are those two values the same? No. And that is the issue with this one. So that the limit as x approaches a of f of x does not equal f of a. So just wanted to give you some examples of how discontinuities can arise and that they can arise in different ways from the different parts of the definition. So after looking at that, we might think about, well, where would we expect to see a discontinuity? I mean, when does a limit not exist? Let's start there. So when the limit as x approaches a does not exist, and when does that happen? So it definitely happens at vertical asymptotes. But where else does it happen? It sometimes happens at like a break point of a piecewise function when the equation jumps. So possibly at breakpoints of piecewise functions, you might have a left-hand limit and a right-hand limit that aren't the same. So then you don't have a two-sided limit. So that's the first kind of consideration. What about when f of a does not exist? That's when you're basically looking at the domain. So at numbers excluded from the domain. I mean, if you were talking about, let's say, tangent of x, you know that tangent of x is undefined at various x values, pi over 2, 3 pi over 2, etc. So it's definitely going to be discontinuous at those places because there is no value for the function. And then the last option is when the limit does exist and the function does exist, but the two are not equal. I think so this is kind of setting up a few different options. So the limit does not equal. And we've kind of already talked about where that might happen, like at breakpoints of piecewise functions. But I guess the other place that it could be too would be like a filled in hole, where the hole is filled in somewhere else, like in the third example up here. You have a hole and then it's filled in somewhere outside of the hole. But honestly, if you were to see this in an equation form, it would be a piecewise function. It would have an equation for everywhere except for a, and then a different value for x equals a. So even in that situation, it kind of still applies to breakpoints at piecewise functions. So if you're kind of analyzing, well, these are the different places we might have discontinuities. If you were asked to figure out where is this function discontinuous and you were given its equation, it looks like we could summarize the above by first looking at the domain, right? We need to find all the points excluded from the domain, because that is going to hit here. And of course here, vertical asymptotes are not going to be in your domain. And then the second thing that you might need to do is look at analyze breakpoints of piecewise function. If you're dealing with a piecewise function, you need to figure out if the limit exists. You need to figure out where the function is defined and if those two things are equal. So there is a animation demonstrating these things. I think I put it on a link to this in the canvas where you can kind of view the various types of discontinuities of this function and get a better sense of kind of how they work. So I encourage you to look through that. We're going to go ahead and answer a few questions, look at a few examples. Where are the following functions discontinuous? Okay. So remember what we were just talking about. Essentially, we've got to start by looking at domain. Okay. And then if it's a piecewise function, we need to go further than that. So this is not a piecewise function, number one, and it's a polynomial. So what do we know about its domain? Its domain is all real numbers. And so this means that the limit as x approaches a of f of x is going to equal f of a for all x values. And so the conclusion we can draw here is that polynomials are continuous everywhere. And that is one reason why in math we often like to work with polynomials. I don't know if you've ever heard someone say that they're well behaved, and they are. They're considered functions that are nice. One of the reasons is because they're continuous everywhere. They're defined everywhere, and they're continuous everywhere. Okay, so let's look at number 2. We have looked at this function a number of times already, but it's back. G of x equals x squared minus 1 over x minus 1. So in terms of thinking about domain, of course, we need to figure out when the denominator is equal to 0, right? The denominator is equal to 0 at x equals 1. So it is G is undefined at x equals 1, which means it will be discontinuous there. What about everywhere else? What is that function going to look like? Well, we've done this a couple times now where we've simplified. I'm not taking a limit, so when I cancel these and say that this is equal to x plus 1, I need to be sure to include that x, I'm sorry, I wrote -1, and I meant 1. That this function will be equal to the function x plus 1 everywhere except at 1. At 1, you're going to have that hole poked out of the line. So this is actually pretty much the equation version of this second picture. X plus 1 everywhere except for right here at 1 with the hole poked out. So it will be continuous everywhere else because everywhere else it's a polynomial. Okay, so it's got a discontinuity. How did we phrase this? These directions. Where are each of the following discontinuous? So they've got a discontinuity at x equals 1, and that's enough. Okay, looking at number 3, now we do have a piecewise function. So the first thing you want to do is just look at each one individually. I have the first equation, x plus 2. That's a polynomial. So it doesn't have any domain issues. It will be continuous everywhere that it's defined. So I look at the second equation, x squared minus 2, also a polynomial, also continuous everywhere it's defined. So I'm just going to put a little note here. Both equations are polynomials. Shorthand a couple words there. So each individual piece is going to be continuous. The question is, what about the breakpoint? We have got to check what's going on at x equals 1. Okay. Now, I'm aware that you could draw a graph of this, that kind of thing. But what we're asking you to do when we're saying figure out if it's continuous here is for you to show the work. Again, demonstrate via notation and analyzing the function on paper about whether or not it's continuous there. So you need to check, is the function defined at 1? You need to check, does the limit exist? And since it's a breakwise of a piecewise function, you're going to need to check the two one-sided limits. We talked about this in a previous lesson, but I'm going to mention it again. That doesn't mean you scribble down this number equals this number, so we're good. You show with the correct notation and the correct functions what these two side limits are. So let me demonstrate. I'm going to start by figuring out that the or equal to is here, so that h of 1 is equal to 1 squared minus 2, which is negative 1. So the function is defined at the point, and it's equal to negative 1. So the next thing I'm going to do is I'm going to take my limits, and I need to do limit from the left, and I need to do the limit from the right. The left side limit would be when x is less than 1. So I'd be dealing with the x plus 2 equation, which I can do direct substitution. The limit from the right is going to be when x is greater than 1. So I'm going to be dealing with the x squared minus 2. And again, I can plug that 1 directly in. And so from these, I've done my two one-sided limits. Notice how I have written it. I have written it so that you understand from reading this that the 3 is the one-sided limit from the left, and the negative 1 is the one-sided limit from the right. I didn't just scribble over here, 3 does not equal negative 1. Because these two numbers, without any other sort of notation, right, do not mean anything. And this is not how we want to write it. We've written it so that the limit notation is clear. You can see what the two one-sided limits are and where they came from, which equations they came from. So now I'm going to draw my conclusion that the limit as x approaches 1 of h of x does not exist, because I can clearly see the two one-sided limits are not the same. So therefore, we can stop here. H of x is discontinuous or has a discontinuity at x equals 1. Okay, I've got one more example here. This is kind of a different function, maybe a function you've never worked with before, but it's a very kind of interesting function to look at. It has this sort of strange box notation, and what it stands for is the greatest integer function. And what that means is that when you plug a number into this function, what you get out is the largest integer. Remember, integers are whole numbers, positive, negative, 0, that is less than or equal to the number that you put in. So let's think about just putting in a couple values. What if I were to put in 2.9? So I need to figure out what is the largest integer, whole number, that's less than or equal to 2.9. That would be 2, right? If I bumped it up to 3, I put f of 3, then my answer would be 3, right? Because that's the largest whole number less than or equal to 3. Now, what about if I put in negative 3.1? Sometimes negatives screw us up a little bit. Negative 1, 2, 3. So negative 3.1 would be right here. What is the largest integer that's less than or equal to this? Less than are always left on the number line. So I couldn't say negative 3 because that is slightly larger. It's closer to 0. But I would have to say negative 4. Okay, that is the largest number integer less than or equal to negative 3.1. So what I want you to do right now is press pause and see if you can graph this. Just out of ease, I found that it was easier on this grid to maybe give yourself, so it's just easier to read, to give yourself 2 boxes per integer. So I'll give it a try. See if I want you to press pause and really think about it. And just start by plugging in numbers and see what you can make of this graph. How did it go? So I think it might be easiest to start with the positive numbers. So think about, I'm going to look at here at any whole number. It'll just be equal to itself, right? If I plug in 0, what's the greatest integer? Less than or equal to 0, or less than or equal to 1, or less than or equal to 2. It'll obviously be itself. So then what happens as I look at numbers between 0 and 1? 1/2, 1/3, 5/8. The largest integer less than or equal to that is going to be 0. So it's going to be 0 all the way up till we get to the 1. And then when we put in 1, it's going to jump up to 1. And then everything slightly bigger than 1 between 1 and 2, 1.1, 1.5, 1.7, 1.9999. The greatest integer that's less than or equal to those will be 1. So it's going to be graphed here at 1 until we hit 2. And that pattern will repeat. And it repeats the same way for the negatives. Okay. This is actually called a step function because it looks like a pair of steps going up. It's one example of a step function, if you've ever heard of that. So now that we have a picture, it's pretty easy to discuss its continuity. You can tell just by looking at the picture. Where is this going to be discontinuous? It looks like it's fine, continuous everywhere in the middle of these steps, but at every place where it jumps from one value to another, then it's definitely going to have a discontinuity there. So if we were to write that down, capital F of x is discontinuous at every integer because the limit as x approaches a of f of x does not exist at these points. And the reason for that is that the two one-sided limits are not equal. And I'm not writing that down analytically because we just drew ourselves a picture and we could see that. So not a function you've used regularly before, but kind of a cool example to think about and to see how continuity could work. All right, last but not least, I think I said that, but I had one more example. You'll see these a lot, these kinds of problems. They were very popular if you took calculus in an AP class in high school, where they give you a piecewise function and they say, find the value of this constant that will make the function continuous. So what they're really trying to get you to do is to set up the one-sided limits at this breakpoint. And if it's going to be continuous at that point, then those one-sided limits have to be equal to each other, right? So we're going to approach it similarly to what we have been doing so far. We're going to do the limit as x approaches 1 from the left, which will be this 7x minus 2, and the limit as x approaches 1 from the right, which will be this kx squared. Okay. We'll plug in our 1. And so here are our answers for our two one-sided limits. As we approach 1 from the left, the limit is 5, and as we approach 1 from the right, the limit is k. So our conclusion will be that k must equal 5 so that the limit as x approaches 1 of f of x exists, that those two one-sided limits will be equal to each other, and therefore that limit will exist, and it will clearly equal the function value at that point, since that function value is just the same as this limit. Okay. So when they're asking you to do that, find a missing constant that will make this continuous, you're back to the same thing you were doing before with piecewise functions at breakpoints, calculating the two one-sided limits and setting them equal.